Hello, this is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School, and I want to welcome you to this lesson on paired data. It is a short lesson, but you will need your calculator during this presentation. So, suppose that you have been hired by a pharmaceutical company to test whether weight loss is attributable to a new drug that is supposed to enhance a person's metabolism. Two observations are collected from each subject, one on the day before the drug regimen began, and then again 6 months later. So this is a classic fact pattern for a paired t-test. We have one sample, but for each subject we're collecting two observations, two response variables. And that's the basic fact pattern for this type of problem. Study designs that involve one sample but take two observations from the same subject yield paired data. An experimental design in which the same participant is observed under more than one treatment, for example, pre and post-treatment, is said to be dependent samples or related samples. So here we have one sample, but we're recording the same response variable twice. In this case, it's pre and post-treatment, but it could well be before and after, sitting and standing, or something like that. But we have one sample, we have two response variables for each subject, and that's the data that we are going to use. Matched pairs can be thought of as one sample of pairs. Once the difference between the pairs of values are found, inference for significance testing proceeds as for a population mean. The null hypothesis is that the mean of a population of difference scores equals 0. So in the process of doing these problems, we're going to have to define a new parameter, and in this case it's mu difference. It's defined as the score of the post-test score minus the pre-test score, and our null hypothesis is that the difference is 0. If the conditions for inference are met, we can use the one sample t procedure to perform inferences about the mean difference mu. This is called a paired t procedure or a paired t-test. The calculation is exactly like what we've been doing in so far this chapter, except that this exactly the same as for a population mean, except that the data are difference scores and the mean and standard deviation are based on the difference scores. In a paired t-test, there is just one parameter. It is the true mean difference. And then we're going to apply the one sample t procedure to the differences. So let's do one of these. For their second semester project in AP Statistics, Libby and Catherine decided to investigate which line was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during a week, went to the same store, and bought the same item. However, one of them used the express lane and the other used a regular lane. To decide which lane each of them would use, they flipped a coin. If it was heads, Libby used the express lane and Catherine used the regular lane. If it was tails, Libby used the regular lane and Catherine used the express lane. They entered their randomly assigned lanes at the same time and each recorded the time in seconds it took them to complete the transaction. So the question is, carry out a test to see if there is convincing evidence that the express lane is faster. So since we're looking to see whether the express lane is faster, I know that this is going to be a one-tailed test. So problems like this will also give us data. Unless they tell us the mean and standard deviation and the number in our sample, they're going to have to give us some data. And here's our data. So we've got 15 observations for the express lane and 15 observations for the regular lane. I'm going to ask that you stop the video right now, get your calculator, go to module number 2, and I want you to put in the express lane data in list 1, and put in the regular lane data in list 2. So go ahead and stop the video, put in the express lane data in list 1 and the regular lane data in list 2. So I'm going to proceed though. So what we're going to end up doing here, since we have these two columns of data, I'm going to have our calculator tell us the difference, and that's going to be this data right here. And it's this data, this red column of data here, that we actually perform our t-test on. After we calculate the difference, we basically can ignore the original two columns of data, and we're going to work with just that column of differences. So here we go. The identify section. In the identify section, we always define our parameter. Tell me the alpha level and state our null and alternative hypotheses. So in this case, I'm going to define mu diff as the true mean difference in the time required to purchase an item at the supermarket. And it's important to define the order of subtraction. So I'm going to say, I put in my definition regular minus express. And we're doing a one-tailed test, so I add this comment here. In this case, a positive difference means that the express lane was faster, and we're looking for convincing evidence that the express lane is faster. So I know now that my alternative hypothesis is that mu diff is greater than 0. So I finish it off, I write my significance level, I write my null and alternative hypotheses. Now we have to test our conditions. The name of this procedure is called a paired t-test for the mean difference. And I want you to cite that name, put that name in your FRQ answer. Random. A random sample of times was taken, and the students were assigned randomly to lanes, so that condition is met. 10%, since we randomly selected the times to conduct the study from an infinite number of possible times, the differences should be independent. So we can really only consider them independent because we have an infinite number of possible times. Then we have to get to the normal large sample condition. We're not told the shape of the parent population of differences, and we don't have a sample size greater than or equal to 30. Our sample size is 15. So we have to draw a graph, and I've drawn two graphs here, a dot plot and a normal probability plot. And we're looking for strong skewness and outliers, and we do not see strong skewness or outliers here, so we're going to proceed. You can say you have to document that you do not see much skewness and there are no outliers. So it is reasonable to use T procedures for these data, or else you could just simply say it is reasonable to proceed. Now we have to get our calculators out, and remember now we have the express data in list 1 and the regular data in list 2. And we want to have our calculator compute the paired differences. So I want you on your calculator to navigate to this column, the column heading of list 3. So navigate so that the black box is over the word list 3, and then enter shift right here, shift, and then the number 1, and that'll give us the list, and then type 1. So we're typing in, then we type 2. So it's going to be shift list 2, and then I hit the minus sign, and then I want to insert list 1, so I'm going to hit shift, the number 1, and then the number 1 again, because I want to take list 2 and subtract list 1. And when I hit execute, it'll populate this third column right here with the numbers that we have in this column right here that I did by hand. Okay, so now we have the data that we want in list 3, and we just need to make it set so that we can perform our t-test calculator function on list 3. I go to module number 2. We're going to follow the instructions for a one sample t-test like we did earlier in one of my lessons. So we input. This data is coming from a list, so make sure you have list here. The alternative hypothesis is that the parameter is greater than the hypothesized value, so set it like this, strictly greater than the hypothesized value. The hypothesized value is 0, and make sure that it says that the list, we're using list 3. Our data is coming from list 3 because that's the data that we're using on our calculator. So when I do that, I hit execute, and it returns the t-statistic, my p-value, my x-bar, and my s of x. So write those numbers on your answer sheet. We're going to start out by writing the mean. The sample mean is 42.7. The sample standard deviation is 84.0. I'm now going to go ahead and calculate my t-statistic. I could write the formula in symbols, but that's not necessary. I just go ahead and write the formula with the numbers from the problem in it. My sample mean is 42.7 minus my hypothesized value of 0, divided by my sample standard deviation 84, divided by the square root of 15, and that gives me 1.97. You're welcome to draw a t-curve and label 1.97 standard deviations above the mean. But we still need to calculate a probability. You could just go back here and say that the probability was 0.0347 based on your calculator with the degrees of freedom, and then specify the degrees of freedom. Or you could use your TCDF function here. Now, whenever we're using a t distribution, we have to state the number of degrees of freedom. And in this case, degrees of freedom is 15 minus 1, our sample size minus 1, gives us 14. We're looking for the probability of getting a t statistic greater than 1.97. So my lower boundary is 1.97. Upper boundary is some arbitrarily large number like 1,000. Degrees of freedom is 14. I hit execute and it tells me that the probability of getting a random t greater than 1.97 is 0.0347. That's exactly what my calculator gave me on this page as well. So that's confirming my conclusion. I now have to interpret that probability. Since the p-value of 0.034 is less than the alpha value, my significance level of 0.05, we reject the null hypothesis. There is convincing evidence that the express lane is faster than the regular lane. So because the p-value is less than our significance level, we rejected the null. That's convincing evidence in favor of the alternative hypothesis, but we have to express the alternative hypothesis in context. So that's the end of my presentation. Thank you very much for listening.